Welcome, and we're going to talk today about thin layer chromatography and our experiment, which is the analysis of a drug component. Our scenario this time is we've had a patient who's swallowed a large number of drug tablets, and what we're going to try to do, he's suffering from an overdose. The bottle, of course, is missing, but there were some unused pills left in the bathroom. The patient's spouse recalls seeing some over-the-counter analgesic drugs in a medicine cabinet but doesn't know what was on the label. There is no toxicology lab in your town, and they have called our organization and asked us to do a quick analysis if we can. So what we're going to be doing is you're going to have one of 6 different drugs. You're going to have Advil, Anacin, which is a mixture of aspirin and caffeine, aspirin, BC tablets, which are aspirin and a chemical called salicylate, and then caffeine. By the way, salicylate is now illegal, so I have to fake this drug. If you go buy BC tablets now, which are available, they now have had the salicylate removed. It has become illegal now. Tylenol, which is acetaminophen, and Excedrin, which is aspirin, acetaminophen, and caffeine. So what you're going to be doing is running the concept of thin layer chromatography, which essentially, if we look at what it is, if I can find there it is. There's our picture of the thin layer chromatography apparatus. So what you will have is a beaker. You will have the piece of chromatography paper, which isn't really paper, it's a piece of plastic with a chemical painted on the plastic, and then what we will have is some solvent in here, and our chemical is going to be that's going to be our different drugs that we're going to test. So what we'll do is we'll make these spots of the various known drugs on this pencil line along it across our piece of chromatography TLC paper. I'm going to call it paper even though it isn't actually a piece of paper. A lot of times they paint this chemical on glass, and it's a lot of times the easier name for it rather than paper would be plate. And then we need a lid on this, and your lab also tells you to add a wick. And if I could draw that wick in very simply, you're just going to take a piece of filter paper, cut it into a strip, and when you cut it into a strip, what you can do with it is, I'll just show that in here, hanging in here, and you hang it over the side of the container. So if you looked at that, that would be a piece of, just filter paper cut in a strip like that, hanging in there. And what that does is, when this solvent soaks up that paper, it fills this, and you need a lid on this, it fills the chamber with the vapor of the solvent so that the paper stays moist as you're doing the experiment. So what the principle is based upon is that there is an attraction between the solvent and the chemicals that you put on the paper, and then there's also a attraction between the chemicals and the TLC plate material. So you have two opposing forces here. You have the chemical being attracted to this, and by the way, this material is made that it will always soak the solvent up. So the solvent's going to rise up the paper as time goes on. You're going to want to let that get, somewhere close to the top, but not near the top. I mean, don't let it go all the way off the paper. And sometimes, if you're watching this thing move up, and you see it all of a sudden quit moving, if it's only maybe to here, still stop it. Don't sit there and let it go, because what's actually happening is the solvent front won't go any farther, but your dots will move up the paper. So if you had a mixture here, what would happen over time would be different components of this mixture are going to move up different rates based on their attraction to we call the material painted onto the plate the stationary phase. The stationary phase, I'm not going to be able to write that. And, well, I can if I get my pencil. And there we go. And then we call the solvent the mobile phase. The mobile phase. So you have your mobile phase, you have your stationary phase. There's attraction between the two at different rates, and what's going to happen is if you have one of the chemicals, the drugs that's a mixture, then you're going to get your dots, you're going to see several dots. Some of you that only get the one drug component, like the Advil or the aspirin, you're only going to get one dot. Now you're going to run all of the known chemicals. Then there are 5 of them. So what you're going to need are 6 dots across the bottom of your paper. The 5 known drugs and your unknown. Now the bad part about it is these dots, when you put your chemical on there, you will put it onto this line, and make sure you watch the video about how to spot the line and how to draw these, and you must use pencil. Do not use pen, because a pen will actually interact with this. And you're going to draw that line, you're going to put that dot on there, and you're going to put it on there 2 or 3 times each time so that you make sure you got a lot of chemical on there. But you don't want you don't want a ton of chemical on there, or it's going to move in an uncontrollable manner. And if the dots get too big, they'll intermingle with each other. So you want a nice dot, you want to blow on it, let it dry, and then put another dot on top of it, and then put your next dot. So across this paper, you're going to end up with, obviously this paper is not wide enough, but you'll end up with 6 dots across here. Now the bad part is when these dry up, you're not going to be able to see them. When these things move up the paper, you're not going to be able to see them. You might, on a couple of them, see a little bit of a place where they've moved up. They're going to be invisible. So there's 2 ways we're going to visualize. Our 2 methods of visualization are going to be, you're going to use ultraviolet light. It turns out that this chemical that's painted on this paper has been impregnated with a chemical that will glow under ultraviolet light. So we'll have a little ultraviolet light that you can shine over the top of it, and then you'll be able to see some, if not most, of your dots. What you want to do, because they're invisible, is take your pencil and draw a circle around all your dots that you see. And then turn off the ultraviolet light, and then you'll see those dots. And then our second method is we're going to use iodine. It turns out that a lot of the chemicals that we use get stained by iodine vapor. So I'll have a beaker that I will have, it will have hot water, it will be a water bath, and there'll be a beaker inside that will have iodine crystals in it. And when the hot water warms this, you'll get iodine vapor in here. And you'll just take your paper and dip it into that beaker for maybe, 20, 30 seconds. And then what you're going to want to do is, if any new dots show up, you're going to want to circle them. So maybe this dot shows up here now under the iodine vapor. By the way, it'll stain them terribly. Now, some of the chemicals will stain and some won't. So you may have 2 chemicals that travel up the paper the same distance, but one of them stains and one of them doesn't. So make sure you write yourself a note that it stained it. And then your lab is real simple from there. You just compare your unknown dot to the known dots, and you tell me which drug you think that you had. Very simple experiment, probably the easiest one that we do. And it doesn't take really the spotting of the chemicals takes longer than anything else. And you just sit around and you wait. My suggestion is, while we call it developing, as it's moving up, we call it let it develop. While it's developing, that's when I would take the quiz. Just, unless you want to get the quiz out of the way first, that's up to you. But while it's going to take it 10 minutes probably to develop, usually 5, 10, at most 15 minutes to develop. So then that's it. That's the entire experiment. And but there's going to be some calculations you're going to have to do, and those calculations are going to involve what's called the RF factor. And in essence, what the RF factor is it's the distance that a particular chemical travels up the paper divided by the distance that the solvent moves. So the solvent will always move more than any of your chemicals. If you leave it on there too long and it develops too long, some of your chemicals will be with your solvent front. You really don't want that to happen. That's typically bad. So for the most part, RF factors should always be a decimal. They should never be more than 1. So for example, if you had a solvent front that was here, so you're going to measure from your pencil line where your solvent started to this is where the solvent front is. So that's this bottom distance here. And then let's say your dot's here. Well, you're going to measure from here to here, and that's going to be the top number. So you'll have to do that. And by the way, the best way to do these is measure to the center of the dot. And that's typically the theory is measure, or the method, excuse me, not theory. The method is to measure to the center of the dot. So you can, once you've got your dots drawn, you can draw a little line through the center of the dot, and then just literally with a ruler, just take a ruler and measure the distances and divide them. So make sure in your report you give me you give me your unknown number. You give me all your RF factors, your ID of your unknown, and of course your reasoning on why you think so. So, those are the major components of the report that you give me. Questions for this one would be number 1 and number 2, number 3, and number 6. 1, 2, 3, 6. So enjoy, and I will see you guys Thursday.